back in lecture 3, we talked about the rock cycle and how we take and process rocks into different things. We could take them and bury them where they get undergo diagenesis. We could bury them even further where they're hotter and under more pressure and metamorphose them, even eventually melting them into magmas. But it sounds like I'm moving rocks around and putting them in different environments. How does that work? So more context into how these processes back from lecture 3, how they work, is plate tectonics. And this idea underpins all of our understanding right now of how the things on the earth work. I'll give you a short story as an example. When I was doing my undergrad at West Georgia in geology, I had a professor, actually probably my favorite professor, but don't tell the others that, Dr. Tim Chowns. So interestingly, Dr. Chowns had finished his education over in Newcastle, England in the early and mid 60s. And so he talked to me about finishing his dissertation, his big seminal presentation, and then having to go back and modify everything he knew because his dissertation predated accepting generally plate tectonics. And so there were things in there that didn't work, and they were reaching to try to make them work. So he basically, after getting his doctorate, had to go back and change the entire way he thought about his field. The science of geology is that recent, and this paradigm shift to thinking about things in terms of plate tectonics is a massive change and really informs how we look at the field. So even though the idea of plate tectonics was not accepted, like I was saying, by the mid 60s, so it had been thought about, it had been talked about, it just didn't immediately get accepted by science as a whole. One of the early things that was proposed was, if you look at a world map and if you look at this bite right here out of the western coast of Africa, and then you look at this piece of South America here, what was talked about was, hey, look, would that just fit right there? I mean, could you just like shove that in and make it part of a bigger landmass? But I think the big barrier to this was in the sense of, okay, fine, but how would you move? How in the world would you move an entire continent? And so we'll get into some of the details of what kept some of this from being accepted until plate tectonics. So just a little bit here about fossils. So it's going to come up, and if you like fossils and like trying to dig them up or look around for them and stuff, geology is a great field for that. And there's a lot around us here in the Dalton area, Northwest Georgia in general, of fossil exposure. So just a few things as we talk through this section that are going to come up. This is a picture of Glossopteris leaves fossils. So the way fossilization happens, the different fossil assemblages, those are more of a topic for the second class in geology, 1122, and I would strongly encourage that. Of course, again, I love it, but I love geology in general. So anyway, if you want to get deeper into the fossil stuff than we end up getting in this course, I would strongly recommend that class. A habit to get into here is things are going to come up, vocabulary terms, and I noticed this time, but there's no guarantee that I always will. So if you look at this right here where I say Upper Permian, so a couple of things about that terminology. Upper to geologists means later, and Permian is a time period. So when I say Upper Permian, I'm saying the later part of the Permian time period. And I won't always remember to talk about this, so get in a habit of, wait, let me go look at that geologic time scale that he told me to keep available and look up when the Permian is. So go do that, look up the Permian period and see when is this we're talking about when These fossils right here are found all across the Gondwana continents, Gondwana being that piece of supercontinent that was several shoved together. And here is that distribution of Glossopteris fossils. So they're found, looks like my drawing shifted off of, but you can kind of see that it was supposed to be part of South America there. I'll have to go back in and fix that. But you can see that they're found in South America, down here in the southern part. And then they were also found in the southern part of Africa. Well, that's interesting because there's like this whole Atlantic Ocean in between here, right? And then they're found in this swath here in India, and they're found on Australia here, well, and then in Antarctica. And remember, this is a global projection of a spherical surface onto a flat page. So this is going to distort Antarctica. We're going to have to distort somewhere, and this is a typical representation. So remember that this part over here is close to Australia, and this part here is close to this here. So those, you could think, well, maybe there's this land bridge idea or something. But then that really gets really hard when you try to explain across this. How could you explain that? And then the same sort of thing for Mesosaurus. They're reported here and here. There's that link across the Atlantic Ocean again. It just seems Lystrosaurus, less exposure, at least initially. Sinognathus, we get distributions across the Atlantic and the Antarctic Ocean. And then here I've shoved all of those different assemblages together, and you kind of see a pattern emerging. We get fossils here, here, up there, there. All right, well, so a simple speculation then, fine, what if all of these are somehow connected when these fossil animals, when they were alive? Now, if these fossils were found in North America and in Asia and in Europe and everywhere else, then you could just say, well, it's worldwide, fine. But they're not. So there's a specific pattern to their distributions. So we have to explain why they are in all these places right here, but they're not in all the other places. And the simplest way maybe to imagine that is to move those continents so that these are the same fossil assemblages I just drew. It's just that the continents themselves have been moved, touching each other, so that Glossopteris, which is the green here, makes this continuous distribution across what was probably its ecological range at the time. Similar arguments can be made looking at structures in the rocks and how the sequences of rocks line up. I want to point out again these time periods. Go and look at your time period chart and see where we're looking at here. And sometimes you'll just see these abbreviations and you have to kind of infer what we're talking about. Devonian. And then this is probably Carboniferous, which on a lot of your diagrams is going to be broken into two different things. Mississippian and Pennsylvanian. That's an artifact of, in North America we tend to talk about Mississippian and Pennsylvanian time periods, and in Europe they tend to lump those two together and call them Carboniferous. They're the same overlapping time periods. And then Permian and Triassic. And UC is probably Upper Carboniferous, which is what we would call Pennsylvanian. So anyway, you start to see some of these related sequences. Like, look, if we look here in South America, we get these intrusives during the Devonian, and then we get some of these clastics and mudstones, and then eventually we get these ash layers on top. Well, and then Hey, look, in Africa we get those intrusives again, followed by those clastics. Hey, this is looking similar to what we saw in South America. And then let's look at India. Yeah, there's our intrusives and clastics, and we start to see a pattern emerging. Well, if all those are the same and the fossils were the same too, maybe we're talking about all of this being connected at some point. You can make similar correlations across other places. I don't know if you've heard before about the idea that the Appalachian Mountains, and especially the structure patterns we see, the folding and faulting that we see along the Appalachian Mountains, well, it continues right up in through Ireland and Scotland. And then it also continues right up through Scandinavia. And just the patterning is strikingly similar when you start doing the mapping. And you're like, well, look, this and this, but they're so separate. So the idea might be, if you move the continents around, it might make sense for it to all be continuous like that. So remember that that's what we're trying to do, is make sense of evidence that we have in the geologic record. So then enter the idea of paleomagnetism. So big word, but what it means is magnetic signature left in the rock from past time periods. And there are some good videos out there on the links on the lecture page. Take a look at some of those that talk about how these work. My initial exposure to magnetic detection was not for tracking geologic structures, but was for tracking submarines in the Navy. So we still used, I have to use past tense there because I have been out for multiple decades now, but at least when I was in, we still used magnetic anomaly detection. We would fly P3 planes towing a detection thing behind them, and they could see through a distortion of the magnetic field when they crossed over a big metal object like a submarine, and we could use it to track those things. Well, apparently we were doing that in World War II, it looks like, and we were starting to map the seafloor and to map the magnetic anomalies. And it turns out that they started to see patterns. And so look at these patterns emerging here. What's going on? I'm going to zoom in on that on the next slide. You see these belts, and in one of these belts, the north arrow of your compass would be pointing north towards the North Pole. That makes sense. So when it solidifies, it'll line up. But then in the next pattern over, it's pointed the wrong direction, backwards, and then back to the correct way, and then backwards again, and you get these stripes. And then to make matters even more interesting, they're not exactly parallel. These point in a slightly different direction than these, and that's where we get the idea of polar wander, and how it looks like what looked like north if you were standing here when it was formed, and what looked like north when you were standing here when it was formed. They flip back and forth, north and south together, but then they start to have a slightly different angle as we go through, and they start to think, well, if we move those continents again, we can make it all line up. All the evidence seems to be getting in the same spot. Okay, so the idea that you could just make everything work out better if you slid these continents around, that met a lot of resistance, and folks were like, fine, you can cut them out as pictures and move them around, but how are you going to really do that? And Wagner's hypothesis is not really accepted during his time. Now, some of that comes from some of the stuff he proposed with it, and we might can talk about some of that some too. But what I want to do with this is, before you get into the next lecture, what I want you to do is go in the discussions and post what you think to be a reason folks would use to not accept this plate tectonics idea? What would be a barrier to accepting that? And what we're going to kind of reach into there a little bit is the scientific process and how paradigm shifts, like that story I told you about with Dr. Chowns at West Georgia, how do those paradigm shifts happen? Why do they take 100 years to happen? So what I want you to do is go in and post first. Start you a thread with, I think a barrier would be, and list what you think it is. What would be a barrier to accepting this? Then I want you to go to your chosen textbook and I want you to read through about plate tectonics. Come back to the discussion boards and find not your own but someone else's reason, someone else's barrier to accepting this, and I want you to answer that barrier from what you've read in your textbook, and then we'll go on to the next lecture from there.